Chris, you're going to be talking about ASM. Take it away, please.
Thank you, sir. So, just when you thought you couldn't hear anything else about multicast, here I am to tell you all about multicast all over again. That is a very sensitive button. So ASM, there's a better way. So ASM stands for Any Source Multicast, and that is essentially, if you're looking at a switch, referenced as a star comma G. There's also S comma Gs, that is a source and group multicast. So just a bit of background about what we're going to talk about here. We're going to go over a brief overview of PIM Dense Mode and PIM Sparse Mode. Then we're going to talk about something new called PFM, or PIM Flooding Mechanism. Then we're going to talk about PIM Flooding Mechanism source discovery and how that works. And then talk about some practical uses and some deployments of this, and the status in the IETF and some projects that we've been working on. So I hope you don't use PIM Dense Mode in your media deployments, but just in case you do, it's the oldest multicast routing protocol technically used today. It's RFC 3973. It was an experimental protocol, not a standard. So this is a flood and prune mechanism. Data packets are flooded everywhere to create multicast state throughout the network, and then pruned back from branches on the network where they're not interested in receivers. All the routers in the domain have all the information about the sources. So this was actually the nice part about PIM Dense Mode, was that you had source and multicast state all the way across the network. There's no single point of failure. Now this is key. A rendezvous point is a single point of failure. It also works reasonably well with a number of low volume sources. And I say low volume, I mean really low volume. You would never send 2110 across PIM Dense Mode because you're going to flood 1.5 gigs, 3 gigs, 12 gigs across your network. Not really used today other than in some very specific fields, and in fact, some switches out there have actually depreciated dense mode. So the way that works, just from a graphical representation, is initially, data gets flooded everywhere on the network. Your actual multicast data will go and flood itself between every router in the network, every which direction, until finally it's everywhere, including the receiver. And then it'll flood a little bit more if it hasn't gone everywhere. After that, we need to prune where it's not needed. So prune is going to be sent to all the downstream interfaces that need to be in a prune state. Data packets are then previously flooded, and prunes are repeated until that state refresh is used. And then now all routers specifically have an SG state. So here we can prune our tree and have only the data tree that is actually required for that receiver. Now, this is not just management messages or anything like that. This is your actual multicast data that gets flooded everywhere. At the end of it, you do have your optimal tree, which is what we want, but it took a lot of time to get there and a lot of multicast data. So PIM Sparse Mode was created. This is traditionally used with ASM and was originally invented for ASM. Multicast traffic is only sent along a specific path to reach the intended receivers. So Any Source Multicast, you can have multiple receivers for a multicast. I'm sure we all know that. You can have some people send out to the same group. But when you're doing ASM with PIM Sparse Mode, originally you would do a star comma G join, which means you join every single sender that is participating in that group. So source discovery is actually done using the concept of a rendezvous point. So a rendezvous point is a specific router on the network that you elect to be this RP, and it acts as kind of the joining point of all the trees. So all the routers in the PIM domain need to know about the rendezvous point's location. So the way that this works is this receiver here needs to do a star comma G join for a multicast. So it's going to send that star comma G join to what we call the last hop router. That last hop router is then going to send a PIM join up to the RP. Then we're going to build a shared tree from that RP to that last hop router. Now, the traffic could technically flow before this point, but in case it hasn't, now I'm going to start sending traffic. Once traffic hits the first hop router, which is the first router closest to the source, we're going to send what's called a unicast SG register towards the rendezvous point. That unicast SG register then sends an S comma G join back towards that first hop router. It's going to build a source tree, and then it's going to stop that register. At this point, traffic will flow all the way down to that receiver. That's extraordinarily complicated. Now, at this point in time, you have two options depending on your network configuration. You can either stay with this traffic setup, or you can cause an interruption and switch to a source tree directly from the first hop router to the last hop router, or a shortest path tree between these two. That's an optional configuration, but in default state, you're going to cause an interruption there and switch. Now, after that, we've got to talk about why that's a problem. So it's complex. but eventually forwarding becomes optimal. And stable packets are, or as long as stable packets for those PIM registers are sent frequently enough and the multicast traffic is sent frequently enough, the rendezvous point tree is built using star comma G, even when no source is present. So if you do a star comma G join, that rendezvous point will register that join towards your receiver, even if you don't actually have any traffic of that multicast. The switchover from the source tree to the shortest path tree introduces a traffic disruption. And when the RP goes down, a new one needs to be elected, you're going to have a problem. There are things out there that can kind of help with this failover, like PIM BSR or auto RP, but at the end of the day, it's still an election process, it's still a single point of failure, only one rendezvous point is active at a time. So to show you just on the same topology, because not everyone deploys very simple spine leaf networks, if we use PIM Sparse Mode on this same network that we had before, the receiver is going to do an IGMP join, which turns into a PIM join and heads up towards that RP. And initially, traffic will use a shared tree, which is rooted at the RP. So it's going to send traffic down towards the RP and then down towards my receiver. Now this is great, but then I need to interrupt it, and then I need to prune the data on my shared tree and switch over to my shortest path tree. So we invented PIM Sparse Mode SSM. So there is a subset to PIM Sparse Mode, specifically for PIM SSM. Now, multicast discovery is no longer done in the traditional model with ASM here. The rendezvous point actually doesn't need to be configured if you're using PIM SSM. So source-specific multicast is supported by IGMP v3. It allows the client or the receiver to specify the source. So now we do an S, G join. So I'm sure you've seen the SDP files for 2110. They specify the unicast address and the multicast group. When you do that on the device, it should issue an S, G join. But if you have one single device on the network that does a star, G join, you cannot benefit from SSM in the group that is doing the star, G join from. You can only do one or the other. You can have subsets of both for different multicast ranges. This simplifies configuration, though, for discovery mechanisms. There's no rendezvous point. You can join SSM channels. You can have multiple senders per the group, but you have individual sources. So technically, there's only one channel per SG combo. Only a single host is able to send multicast to that channel. But we don't support star, G joins. So as soon as you have star, G joins, you cannot use this ideal multicast distribution mechanism. And as somebody who's deployed many, many networks and media, I can tell you that there's always at least one device that does star, G. Audio devices are notorious for this. So allow me to introduce you to something that can solve the problem. PFM, or PIM flooding mechanism. So how could we get the benefits of dense mode with ASM and SSM all on the same network? We can create a generic mechanism for flooding information through a PIM domain. So we can use TLV messages to allow new types of information to be distributed, and it includes originating routers' addresses, RPF information in order to check that. All of this can be sent out with TLV messages in the network. So we could flood these TLV messages and inform the rest of the network about anything we want. So if we were to use that for source discovery, we could have a source arrive at a first hop router, and we could take the information of that first hop router and flood out PFM messages once that initial packet is received, and we can forward hop by hop throughout the entire domain to inform every router about the SG combo inside of the network. All the information is cached inside of every router, but we actually don't build state or routing state in the multicast routers until somebody actually wants to join. So I have a source, it sends it here. Now I have a receiver, and this receiver sends a join. That join gets all the way to that first hop router. Since I already know about all the multicast routers in the domain and where all the sources are, I can automatically build that shortest path tree using that cached information and build the state. So that is an optimal, without doing a rendezvous point, shortest path tree built in PIM. So why is this important and why is it cool? Well, it's actually kind of plug and play for multicast. You just have to enable PIM and it kind of works. There's no more rendezvous point configuration, no worrying about who's the rendezvous point of rendezvous points, no more MSDP configuration between rendezvous points. So all the routers now automatically know about all the active sources on the network. but there's no unnecessary data forwarding. So think of PIM Dense Mode, but without the dense portion of it. So you only join trees when that source is available, saving bandwidth for SG joins. You don't have to build that state to the rendezvous point if you join a flow that's not actually there. Gets rid of the RP configs, no exchange of data registers, no switch over from that ST to the SPT, and hence no traffic disruption during that transition. Again, talked about no RPs, so it is similar to SSM, except source discovery is done by the network itself now and not by the individual devices. No single point of failure. It's very robust and resilient. All the routers know about all the sources on the network. There's no single point where all that information is stored. And the best part, it supports star, G. So what happens if a link or router goes down? So if a router goes down, that router loses state. If there exists a path from the source to the receiver after a router is down, then there's no interruption, except for the actual forwarding time to change over which router is sending it, the new convergence, right? So it's similar to other multicast protocols in that way. If parts of the network no longer have reachability to the source, that source discovery state is retained for 3 minutes and recovers as soon as reachability is restored. When a link or router comes up and PIM neighborship is established, neighbor sends the update of their cache discovery state. So as long as you're a PIM neighbor, you can receive that cache discovery state to the next router. And source deliveries are sent periodically, roughly every 60 seconds. So a practical deployment. Everyone has said, well, why would you use this? And I'm not going to lie, PIM Sparse Mode works extraordinarily well for pretty much every SMPTE 2110, AS67, whatever multicast deployment you have, because we're doing spine leaf. And in a regular spine leaf network, the trees are going to be the same. The shortest path tree, the source tree, the PFM-SD tree is all going to be the same because it goes from the leaf to the spine to another leaf. The complexity comes in when you have multiple systems all connected together, or maybe you have a very large multicast domain with multiple systems, or maybe just two completely separate systems you want to share stuff between. MSDP is cool, but MSDP requires rendezvous points. So in this case, I have a fabric at a local production center. I have an entertainment venue that's connected. Maybe there's cameras inside the entertainment venue, multi-viewers, maybe a digital signage system or something like that. And then I have a truck connected. As long as all of these deployments are owned by the same owner and they are in the same multicast domain, I don't have to configure a rendezvous point anywhere or deploy a single MSDP session. Automatically, all of these three entities will know everything about the sources and the multicast groups across the entire multicast domain. You can also have multiple sources for ASM flows without actually joining all of them by accident. You'll do an individual SG join, even with a star, G for each individual source. You can make bandwidth utilization efficient. You don't have any shared trees or rendezvous point, and it's actually faster at convergence. So the status, right? So everyone says, well, what is this? Well, in the IETF, I'm sure we all know what the IETF is. It's the standards body for RFCs and internet protocols. The PIM working group has adopted this item, and it's actually defined in RFC 8364. So if you want to look up PIM flooding mechanism, that's the one to look at it at. 8736 is just some updates to PIM, so I've put that in here as well. It's currently, PIM flooding mechanism source discovery is actually adopted by multiple media entities already, globally. And so far, there have not been any failures. It's very robust, and it's working really well. So with that, I will ask for some questions.
Very good. I see, Wes, are you heading there with a question?
I knew Wes would have a question.
Of course.
So actually, I have two questions. First of all, you're talking about routers here. Is this type of function able to be implemented in a classic layer 3 switch, or do you need a true router?
So when I say router, I mean layer 3 switch, actual router, just router, doesn't matter. Anything that routes multicast, so anything that would have a PIM feature.
Okay, so just an off-the-shelf, okay. Second question, how does this work with 2022-7 flows? How do you handle protection, switchover, things like that? Obviously, each endpoint is going to try to generate two paths to the source. How's that going to work? So
with -7, I mean, it's two IGMP joins, typically, right, to two separate networks. So I wouldn't advise, necessarily sharing sources between the red and the blue network. Typically, people leave those completely diverse. So you're going to have a separate PFM-SD on this side, a separate PFM-SD on this side. Nothing actually stopping you from completely converging it. But really, as long as you do the right join, you're going to get the right multicast. And I don't think, and in fact, I think it's written in -7 that they're supposed to be separate multicasts. I could be wrong about that, but I think I recall reading that.
Yeah, I think they're separate multicasts, but can't they be the same source?
They would be separate source addresses. They would be two separate interfaces on the host, so they'd have different routing source addresses, different unicast addresses. And
Okay.
in every implementation I've seen, they've been a separate unicast address for network
Separate
A and
unicast,
network B.
okay, all right. Okay, that makes sense. Thanks.
Okay, great. Any others? I don't think so. Thank you very much.
No
Interesting.
problem.
Appreciate it.